we should cover most, if not all of that. Hopefully we'll have a big discussion today. I feel like the questions that came up in the quizzes, I can make up examples in SAS. I've got a few examples here on our PowerPoint slides, but I think if we have just kind of a discussion, I've nixed the breakout for today, so hopefully we'll just kind of substitute that just based on the quiz questions. Hopefully we'll substitute that with just discussion. The two big ideas for today are that we feel really comfortable. I guess there's three really big ideas with p-values, what they mean, how to actually do the t-test, and how to interpret it. So I got some of those questions. What a p-value is, how to interpret it. Number two is that scope. I've got a few questions on exactly how to do scope, and that's totally normal at this time. So maybe I can come up with a couple examples for that. And then the last one was power, and exactly what we're doing to get our mind around power, because that's an important issue. By no means do we have to have it all totally mastered today, so if you don't feel like you have it, we're going to be going over this in more depth next week as well. So we'll keep getting more and more examples, but we want to take a big chunk out of it. If not, if you're really comfortable about it today, at least get a really good start so that we can, at least get more than half of it today so that we can tackle the stuff in Unit 3. So we've got 2 weeks on this, basically what I'm saying. We had a question, though. Was it, I didn't see who it was, though. Somebody just asked a question.
Right. This is Ramesh Bivin. Hey, quick question. So at the end of each chapter in the textbook, there are some exercises. Are we expected to do those exercises? I mean, what's general expectation?
I'm sorry, which exercises are you talking about?
Like in the textbook, I know like there are some, questions and some examples at the end of each chapter. So are we suggesting that we should try to do those, or what's the expectation?
Those are great. Those are great practice. Oh, Joshua held them up. Yeah, hold on. Let's look at those again. You're just talking about like the exercise. Yeah, if you're talking about the exercises at the end of the chapter, sometimes the problems I give you for homework will be related to those, or will be actually those. Not completely often. But, I mean, if they're not assigned to you in homework or they're not in a quiz question, they're not required, but they are really good to think about. And, in fact, there are some questions back there that I think are amazing. We'll bring up good topics in here. They are called I'm sure this might be some of the ones you're talking about, conceptual exercises.
I mean, there are data exercises as well.
Right. Well, on the conceptual exercises, it actually has the answers in the book.
Right.
So I don't know if everybody's seen that or not, but if you go to the very end, it says answers to conceptual exercises. I would encourage everybody to go through and do the ones that were relevant to what we were talking about in there, because they are very good at reinforcing the conceptual side of things, which is really, once you understand that, the applied side becomes a lot easier. As far as the computational exercises, again, I would really encourage you to do those, but it would take you a while to do all of them. If you find one that you like, or you've got some extra time, there's some data problems in there too. It would take a really long time to do all of those. So you're only expected to do what's in the homework. But for sure, if you want to get ahead or really get a better understanding, do those, and we can address those in office hours or outside of there. If you want to write one up and send it in, I'll look at it and give you what I think about it. But I think that would be great, but it's definitely extra on top of what you already have to do. But something that's quick and easy are those conceptual questions, and the answers are in there. So you can kind of get an idea, think about it, and then go back and look at it, and then we can bring it up in a live session as well. So, all right. Okay, great. Any other questions or comments on the way into our discussion today? I'm going to go through a few examples, bring up your questions as they come up. Again, the big things are making sure that we understand how to actually run a 1 and 2 sample t-test. Along the way, I'll break it into the sides, 1 and 2 sides. I imagine we'll have some questions there. And then number 2 is scope of inference, and number 3 is power. So that's plenty to talk about today. And again, office hours, you can write this down. I'll post it. Dang it. You know, my camera just, I just lost my whole internet connection. Uh-oh. Hang on one second. We're having technical. Oh, no. Well, my internet connection just evaporated. I think somebody just shut the whole thing down. Huh. Interesting. So, I don't know what to do with that. What I think might be happening, you're going to have to excuse me for one moment. I really apologize. I think I'm going to have to run. I'm in my office right now at work. They might be, I don't know what they're doing. They might be shutting down the power in this building. And if they are, I'll just run over to the library and plug in there, and we should have, oh God, we should be able to do that. Okay, so can I do that? Either that, or I can run it off my computer here. I wish I could get you something to do. Give me 1 second while I power up my hotspot on my phone. Bluetooth, Wi-Fi, personal hotspot, that, personal hotspot. Come on. Inside his iPhone. Power. Connect. All right, so I'm just going to go to this thing. Well, one thing you can do that I wanted everybody to do on the way in here, which addresses our first point, which is point 1, is to get a definition of a p-value, and you can guarantee this will be on your exam. The definition of a p-value, if you have a pen or pencil or something, probably want to write this down, is so p-value dash, and we're going to come back to this again and again and again. The p-value is the probability of observing by random chance something as extreme or more extreme than what was observed given that the null hypothesis is true. You can say given or assuming. So the p-value is the probability of observing by random chance something as extreme or more extreme than what you observed given that the null hypothesis is true. And really think about that one for a moment, and that's going to come up in every single hypothesis test we run. Why is this not power? Okay. Okay, so if I can just get into here and go back over there. All right, I'm on my hotspot now. I'm almost there. So we've got p-value. Bring that up, join now. Joining back to our session, which is awesome. hopefully we're still recording and we'll be ready to go. Don't have time to spare, so let's get it on there. I should be pulling it back in. It is connecting. So as soon as we get into this, I'm just going to go straight into an example and we can start talking about it. This will be a one sample test, so not a two sample test. And I know we had some questions about the additive effect. I'll cover that as well. So I am going to actually, for this one, I'm going to turn on my webcam, but I apologize since whatever reason our internet just went out. So I'm off my phone's internet. So I'm going to turn off everybody else's because I think it might crash my phone. So I've started my webcam. You can see me on there, but I thought I just turned off everybody else's, but I don't know. Anyway, okay, good. So there we have it. Let's get going here on the PowerPoint side. And okay, it's running really slow. That's all right, because we just need one thing to come up so we can talk to it. So what I'm going to do here is an example. Again, I did a lot of living in San Diego, and in San Diego, we had this bar called the Beachcomber, and it was just kind of a bar, restaurant, meeting place for everybody. So what I wanted to do real quick is, that's our first example that I'm going to go through. I'm going to skip through this central limit theorem stuff for the most part, but I'm going to give you basically an idea of what it is by just showing you a quick graphic. I'll drop these slides out on the internet, but basically what you're looking at right here is the central limit theorem. So, and I had a couple questions of this on the quiz too. It is, we want to know the distribution of the sample mean. So what does that mean? And it's a concept that takes a little getting used to. What you're looking at here is the distribution of the individual. It's the distribution of just individual subjects. N equals 4 here is if we took a random sample from this distribution up here of 4, randomly selected 4 people or 4 subjects, averaged their responses, and did that again and again and again and again and again. So I just kept resampling. I took a sample of 4, grabbed the average. Took a sample of 4, grabbed the average. Took a sample of 4, grabbed the average. If I kept doing that over and over and over and over again, I would end up with a whole bunch of X bars. And if I looked at those would start forming a normal distribution. But only at 4, if this isn't a normal distribution, that's where the 30 comes in, and that's a very arbitrary number. I can show you certain data sets. It turns out if this is normal to begin with, then samples of size 2 will have this normal distribution. If this is very not normal to begin with, then I'll need a lot more to make that a normal distribution, to make these sample means normally distributed. But it's a totally different thing to think about an individual and a mean of individuals, of course. Now, as I take more, say I take 7 from here and grab an X bar. And then, so let's say that I take 7 again and grab an X bar. And let's say I do that 1,000,000 times. I take 1,000,000 samples of 7, so I have 1,000,000 X bars. Some of those X bars are high. Sometimes I grab just randomly high people from here. Sometimes I get just randomly low people from here. But most of the time I get a mix, especially the bigger the sample I have. Most of the time I get some high and lows. If I get high and lows, they average each other out, and you end up with something in the middle. So again, if I took 10, I start to see a normal distribution, and I also start seeing that it's harder to get big values, and it's harder to get small values. This is going to be huge to our whole idea here, is because I may not know the distribution of individuals, even though that's what I want inference about. I want to know the mean of this distribution. But I may not know the distribution. I may not have as normal or chi-squared or some distribution we don't have a name for. In this case, it looks pretty uniform. But the point is that I don't know what that distribution is, but if I take means from there, then I know the distribution of the means. And so it's very careful, because this always gets said, if you take samples more than 30, you have pretty good idea that the distribution of means pulled from that population are normally distributed. You do not know, and this will probably be on the final 2, or the final and/or the exam. Notice the difference in this question. For samples more than 30, if I sample more than 30 from a population, then subjects from that population will be normally distributed. Think about if that's true or false. if I pull 30 subjects from a distribution, if I pull 30 subjects from a population, then I can ensure that subjects from that population will be normally distributed. And that's simply not true. That is false. No matter how many I take from this distribution, the distribution of individuals will always be normal, or will always be whatever it is, in this case, uniform, no matter how many I pull from this, right? Because I'm talking about distributions of individuals. But if I pull samples of size 30, the means that I pull from that distribution, no matter what that distribution is, should be approximately normal. Let me show you another graph of this. Oh, and one last piece is that the beautiful part, we wouldn't even care about X bar if it wasn't what's called unbiased. And unbiased means that if I took those million X bars, say I took 1 million samples of 4 and grabbed a mean of each sample, I'd have 1 million X bars. X bar is the sample mean. So if I had 1 million X bars and I took the average of those 1 million X bars, so the average of a bunch of averages, some of them are high, some of them are low, the average will be very, very, very close to mu. And if I was able to take 1 million an infinite number of samples of size 4, if I was able to take an infinite number of samples of size 4, take a mean of each, so I had an infinite number of X bars, the mean of all those X bars, the mean of the sampling distribution of the mean would be mu. The exact same mu of the original population. It's this mu that we care about. And it just so happens that this mean is the same. The mean of the sampling distribution of sample means. So that's why when I want to know something about this distribution, I go and get a sample and take the mean, because we know that it's a good estimator of the mean that I care about. Okay, let me show you a different example. So this one is a great plot. This one here says, hey, if you're dealing with a normal distribution, no matter how big your samples are, this is saying if I take 1 million billion samples of size 3, so I have 1 million billion means, it'll be a normal distribution of means. And it turns out that the subjects are also normally distributed. And then as this gets bigger, notice that the standard deviation, every normal distribution is defined by a mean and standard deviation. Turns out the mean of these guys is the same, but the standard deviation gets smaller, which means my estimate becomes better. I get a better estimate the more I sample, which just makes sense. Just makes intuitive sense. So this, what we're looking at here, is huge. Now, what's even better is notice what happens when the distribution of that I'm trying to get inference for the mean for, let's say the population is right skewed. Well, if the population is right skewed, it still has a mean, and I'd like to know inference about that. But I don't know, I can't find p-values, and we'll get there again. But here I have a nice little chart that tell me areas under this curve. I don't have nice charts that tell me areas under these curves, under this curve, under the right skewed curve. So what I need to do, and that's what the p-value is. So what I need to do is say, well, hey, I'll just take a sample of size 3. And if I looked at it theoretically, samples of size 3 have almost a normal distribution. Samples of size 5 are better approximated by a normal distribution, 10 are better, and 20 are even better. And notice that that standard deviation gets smaller and smaller and smaller. I think the one mean that I'm going to pick, in reality, I only pick one mean. I'm hoping that it's close to mu. And down here, it's more likely to be close to mu than it is up here. And notice, we can just skip this. This is the one we looked at before. But here, look at this distribution. I don't know how. A permutation test would be a good idea to find one from here. But it has a mean. And when I start taking samples of size 3, if I did that over and over and over again, look at what I get, something close to a normal distribution. And the more I'd sample, let's say I took 1 million samples, each of size 20. If I took 1 million samples, each of size 20, and looked at the distribution of those means of those samples, those means would have about a normal distribution with the same mean as the mean that I care about, but with smaller standard deviation, which is great. That means I can be more accurate. My confidence intervals get narrower. I can't come back to this one every time. This is really the big picture that we're looking at. And I really encourage you to go to this website here. This website will let you kind of play around with it. In fact, oh, shoot, I guess I'm right. Oh, no, you can't see that. Sorry. So, really, if you can kind of play with that right now if you want. If you want to, well, I guess you don't have that. I haven't posted those slides yet. But when you get this, please go to this, and you'll get a better idea of the central limit theorem. Okay, so I'm gonna skip through this idea. You can kind of go through this. This is a dice rolling example that I made. these are, I guess I'll have to kind of thumb through it. So these are all rolls of size 1. Oh, now I'm rolling to size 2. Well, I guess since I'm here, let's go ahead and go through it. Since I got to flip through them anyway. So if I roll size 1, let's just say that I did this in dice. And if I do this in the dice, and I roll, hang on a second. I think that my histograms are missing, huh? Yes, that's nice. Okay, I think I might be missing. Oh, that's nice. All right, I'm just going to do this. Somehow my pictures didn't come over. But basically what we're saying is this, is if you roll the dice, let's say I rolled the dice one time. Let's say I rolled the dice one time and I recorded it, just like you saw on my screens there. And if I recorded it, but I rolled the dice, say, 6,000 times. If I rolled one dice 6,000 times and record the reading on one dice, I would have 6,000 numbers from 1, 2, 6, 5, 5, 6, 3, 4, 3. So let's say that I rolled it 6,000 times and I recorded only the number of 1s, the number of 2s. You'd probably get something like this. And that would be about 1,000. There's a 1/6 chance, if it was a fair dice, there's a 1/6 chance of getting 1/6 chance of getting a 1, a 2, a 3, 4, 5, or 6. So it would be about a uniform distribution. Probably wouldn't be straight across because there's some sampling error there, right? There's not going to be exactly 1,000, 1,000, 1,000, 1,000, but you get something that looked like that. Now let's say that I took samples of size 2. In fact, you know what? Let's cut to the chase. Let's say I take samples of size 5. Now I'm going to take I'm going to roll my dice 5 times. Picture that. I'm going to roll my dice 5 times, and I'm going to take the average of those 5 rolls. So now I'm not looking at the distribution of individual rolls. I'm going to look at the distribution. I'm going to call that X. I'm going to look at the distribution of means of size 5. So again, I'm going to roll the dice 5 times, take the average. Roll the dice 5 times, take the average. I'm going to do that 6,000 times. So I'm really rolling the dice 30,000 times. But every 5, I'm going to take a mean. So 5, I'm going to take a mean, roll it 5 more times. Take a mean, 5 more times, take a mean. Think about, how likely am I? Am I more likely to get a 3, an average of a 3, or am I more likely to get an average of a 1? And you just think about that for a second. But notice the only way you can get an average of 1, it's hard. You have to roll a 1, 1, 1, 1, 1. And the only way you get a 6 is you have to roll a 6, 6, 6, 6, 6, 6. The way you can get a 3, you can roll all 3s. You can roll half 2s, half 4s. You roll half 5s, half 1s. You can do a bunch of different ways to get that. Turns out the average is a 3. You'd end up with something that looked like that. Every once in a while, I'm going to roll 5 1s. If you ever played Yahtzee, it's possible. Every once in a while, I'll roll 5 6s. So it's not impossible, but notice it's not the same. And in fact, even at n equals 5, the distribution of sample means is normally distributed. That's going to be huge for us when we start finding p-values. Let me go to the last stage here. Let's say that I roll my dice 10 times. And let's say that I do that 6,000 times. So now I'm going to roll it 10 times. Think about how hard it is to get a 1 or a 6. Right? If I did that 6,000 times, maybe it'll happen every once in a while, and maybe it won't happen. You're not going to get very many of those if you get any at all. And you're not even going to get very many 2s. And in fact, what's going to happen is this will be really small, and then all of a sudden, you're going to get something that looks kind of like that, where you get a lot in here, and every once in a while you get some out in the tails. Right? And this is, 3's right about here, and 4's right about there. So what this is saying, hey, this guy has some sort of standard deviation, right? Most every distribution has a mean and a standard deviation. Turns out this one has a mean of 3.5. 1 plus 6 divided by 2. I'm just telling you that. It's got a mean of 3.5, and it's got some sigma. This one here turns out that it also has a mean of 3.5, which is great, right? That's what the central limit theorem tells us, is that the distribution of these x bars is the same as this one. So that's why x bar is a good estimate of the mean. However, I can get closer. I think my x bar is closer here than just some random draw, because this sigma is sigma over the square root of 5, sigma over the square root of n, like you've seen before. And then finally, the more you sample, the more you think that one sample you take. We don't really take 6,000 in real life. We just take one. So that sample that you do take, we think, is really close to 3.5, because if we did it a million billion times, most of them would be really close to the mean. So this one still has a mean of 3.5, but its sigma is sigma of the square root of 10. That standard deviation is smaller. If you want to have a really good estimate of the mean, that's just saying take a big sample size, which is intuitive, but this is mathematically why. That's the picture. That's the central limit theorem. Okay, so we're going to use that, and we're going to blend that in with what we know about permutation tests when we're finding these p-values. And if you would, every once in a while, just go back and reread that definition of the p-value. I can't stress how important it is. And once you understand really what that means, life gets a lot easier. And all these conceptual type questions become easy to answer because we know what those things mean. A p-value is just the probability of observing something by random chance, as extreme or more extreme than what was observed given that the null hypothesis is true. Okay, so let's do that real quick with this beachcomber example. So here's the beachcomber. Oh, that's Guinness. So here's the beachcomber. Basically, what we're talking about here is I observe 7 people coming out of the beachcomber. And if I had my arrow, so there they are. And I just randomly, notice I've said randomly here, so I randomly chose, this is a one sample test, 7 people coming out of the beachcomber. And it's 25, 19, 37, that's their ages. And they wanted to know, the big question is whether or not this was evidence that the mean age was greater than 21. So that's right here. We assume that the data come from a normal distribution and would like to build a 95% confidence interval for the actual mean age of patrons at the comber. So, so what we could do there is come up with, well, and this will come out of SAS too, is what? Is the confidence interval. And so our confidence interval is, as you've seen, is the margin of error is just some multiplier. In this case, it's a z alpha over 2. That's the normal multiplier times sigma divided by square root n. That's if we know sigma. That was another big point here, is that if we know sigma, then we can just use the z. We can just use the normal quantiles. And that, of course, is 1.96. You have a 95%. And 7.808 is what we're assuming sigma to be, and we're getting that. I'm just assuming that we know it to be 7.08, and our sample size here is 7, so that becomes our margin of error. That's our x bar. There should be a bar on that. So 29.86 minus 5.24, 29.86 plus the margin of error. That gives us plausible values for the mean. Those are plausible values for mu. And because we think that our best guess is simply the average of this, which is 29.86. But we don't think that that's actually it. We think that that's our best guess. And if that is our best guess, then put a little bar on that. If that is our best guess, then we can build a confidence interval around that. And our confidence interval is simply built around that idea of the central limit theorem. How sure am I that x bar is close? Where do I think I am on here? How sure am I that I think that x bar is close to the true x bar? I don't think it's exactly. I don't think I'm that lucky. There is some random error there. How's that random error measured? It's sigma over the square root of n. There it is. That is the standard error right there. And z just simply tells you how many of those to go out. And the Z alpha over 2 is based on your confidence. So for 95%, I want to go out about 2 standard deviations. For 99%, I would go out more because I want to contain 99% of the area in here. For 90%, I'd go in less because I'm going to take 90% of that area. So it'd be 90%, 95%, 99%. You remember that from the bridge course or from previous statistics courses, is you have the empirical rule, right? Within 1 standard deviation is 68% of the population. Within 95% is about 1.96 or 2 standard deviations. And within 99% of the population in a normal distribution is within 2.75 standard deviations. So this is a 95% confidence interval. So this number right here is about 1.96, about 2. If this was a 90% confidence interval, that would be about turns out 1.645. Just to give you a reference, if that was 60% confidence interval, that would be a 1. If that was a 99.7% confidence interval, that would be a, because we know that within 3 standard deviations, 99.7% of the population is contained within 3 standard deviations if it's a normal distribution. If it's a normal distribution. So let me bring it all together here. How do we know that this is a normal distribution? How do we know that these means have a normal distribution? Because we knew that the original distribution was normally distributed. Let me bring that all in here. If we did not know that this was a normal distribution, if we did not know that these ages were normally distributed, then we would have to sample at least 30 is our rule for now, is at least 30 to ensure that the means were normally distributed. These ages will always be whatever distribution they are. But if I sample more than 30 from that distribution, we think that the sample means will have a normal distribution, in which case we can use this Z. Okay, so we're 95% confident. You can think of these values, and this is so awesome, right? These are plausible values for the mean. Our best guess is that the mean age is 29.86. But we think that it's plausible, given this data, it's plausible that the mean age could be between 24.62 and 35.10. And that's all we're doing. The mean age could be 37, and we just happen to get a bunch of young people in our sample. But we think that we're 95% confident. We're not 100% confident. We're 95% confident that the true mean age is in this interval. Okay. We've got to have all pieces of that. Please fire away questions if you've got them. But that's where we're at right now. Maybe it seems, well, who knows how it seems, but the whole, so fire in with questions if you have them. But the whole idea here is this is how you form a confidence interval, and the interpretation of a confidence interval is that these are plausible values. For what? For mu. Okay. So now let's see what happens. Notice that this sigma has turned into S. Notice that sigma here has turned into S, meaning we don't know the sample, we don't know the standard deviation. We have to estimate it. And now we're saying, hey, this 7.08, we usually don't know the sigma. I'm just giving you both sides of it. So if we don't know something, think to yourself, if we don't know something, should our confidence intervals get wider or narrower? And you just think that to yourself or fire in. But if we have more uncertainty, should this interval that I just showed you, should it include more plausible values, or should we be able to say it's in a narrower range of values? And the answer there, cool, I like us firing in on the chat over there. So, and this is always, this is great. So this is always the battle. If I have more, and it looks like everything that's on here is right. If I don't know the standard deviation, in fact, I won't draw that. It looks like everybody's got it. If I don't know the standard deviation, that means my intervals will get wider. It means I've got to include more plausible values. And how does that happen? That happens by using the T instead of the Z. That's what it does. T distributions give you wider, notice this was 1.96 and now it's 2.447. This value is the same and that value is the same. It's just when I don't know the standard deviation, this multiplier, I call this a multiplier. It's the same as the critical value in the two-sided test. It's the same as the critical value in a two-sided test, but in a confidence interval, I call it a multiplier. Notice that for the same confidence, it's bigger. It's not 1.96. This one's 2.447. And so that's going to make your margin of error bigger, which when I add and subtract it from the mean is going to make my set of plausible values wider. I'm not as certain of where I can't be 95% confident that I'm in this narrow range. I have to add more. Remember, that was 24 something and that was 37 something, or 34, I don't remember what it was. It was something smaller than 36. This was 24 something and that was probably 35 something. This interval is wider. We have to include more plausible values. I'm less certain of where X bar is. So that's the idea. So, and it just goes with intuition. The more I know, the more narrow it gets. The bigger my sample size, the narrower this gets, because this number here gets bigger. If I know sigma, then I can make that a z, and this number gets smaller, and my margin of error gets smaller. All sorts of things can change that. Another thing is, if you can find a way to make your standard deviation smaller, that would make this smaller. I have a better idea of where my individuals are, and that would also make it smaller. Typically, you can't control this, but you can control your confidence, and of course, you can sample more. Okay, so just a quick look at Z versus T, putting them all in there. Yeah, good, I'm glad I made that slide. So putting them all in there, you can see it. This one's wide, this one's narrow. Why? Because here I'm saying I know sigma, and here I'm saying that I have to estimate sigma. Big, big deal. Very big. So here are, and if you import, this is a good time to go back and look at that bridge course if any of this doesn't make total sense right off the bat. But in this class, I break it down into a 6-step hypothesis test. Some people have 5, some people have 4, some people don't have steps at all. I think it makes it easier to do in 6 steps. So first step is to identify null and alternative, and all this is on that bridge course, so I encourage you to go check it out. And so is the central limit theorem. Number 2 is to find the critical value. Number 3 is to calculate the test statistic. Number 4 is to calculate the p-value. Number 5 is to make a decision. So based on your p-value, you're going to make a decision. And number 6 is write a clear conclusion, use mostly non-statistical terms, and in the conclusion with a statement about the scope if it's appropriate. And a lot of times we'll get there. Sometimes it's not necessarily appropriate. But so these are the 6 steps. Okay, so 6 steps, right? So identify the null and alternative hypothesis. Where did I do that? Hang on a second. Okay, so I'm going to put that on there. So the null and alternative hypothesis for this one is we want to know if HO mu equal 21 versus HA mu greater than, or what was the question again? No, I'll just put it like this. Not equal to 21. That is our null and alternative hypothesis, and you'll see it pop up on these slides in a moment. But that is our null and alternative hypothesis. We're testing mu. Is it 21 or is it not equal to 21? Now, given our, I'll ask you this. How about from our confidence interval? Our confidence interval suggested that given the data, our plausible values were from 23 to 35, or 23 to 36, 95% confidence. So if that's the case, which one do we think the evidence favors? Does it favor HO or does it favor HA if my confidence interval is 23 to 36? And that one would be exactly. So yeah, right on the noggin, right? If 21 is not in the interval, that means the evidence is suggesting that mu, we don't know what it is, but we have plausible values for it, is something different than 21. If 21 was in the interval, then we would fail to reject. Gosh, these are just such big topics coming in early. This is 23, say, to 36. If that is my 95% confidence interval for mu, I'm saying it's plausible. We think it's between 33 and 26. 21's not in there. 21's not plausible, so the evidence suggests that mu is not equal to 21. If, however, let's say, well, in that case that we just did, we'd say we reject HO. That's if it was 23 to 36. If my confidence interval is 23 to 36, I reject HO. I would fail to reject HO if I had something like this. Say it was 19 to 25. If my confidence interval, big if there, if my confidence interval for mu was 19 to 25, that contains 21, and so I would fail to reject HO. Notice that I'm not accepting HO, and that's going to become a really big point here in a minute. I'm not accepting it, and that's a fine point. Like, well, why am I rejecting or failing to reject? Why do I have to use that language? Because this one is suggesting, yes, that mu is not 21. We don't say we're accepting HA, but basically we're accepting HA. We're saying the evidence supports the alternative. That's what we'll always say. The evidence supports the alternative, that mu is not equal to 21. In fact, we're 95% confident it's between 23 and 36. Notice that it would be wrong. Pedagogy says don't say what's wrong, but I'm going to make an exception in this case. It would be wrong to fail to reject HO and conclude that mu is equal to 21. And see if that makes sense, right? A lot of people will say, oh, okay, well, 21's in the interval, so we fail to reject HO. The evidence suggests that mu is 21. That's called accepting the null. And it's so wrong, and it's so deceiving, and can really make somebody make bad decisions. Think about what that says. Does the evidence suggest that mu is 21? And you say, heck no. The evidence suggests that it's between 19 and 25. 21 is one of the values, but it's not suggesting any particular value in there. In fact, if anything, it's suggesting most that it's the middle of this interval, right? The middle of this interval would be, what's that, 6, 3, oh, crap. Well, I happen to make the middle of this interval 21 by accident. So let's go ahead and say that. The middle of this interval, right, 21, oh, wait, no, it's not. So it's 22, good. So the margin of error of this, the distance between these two, 25 and 19 is 6, right? The distance from here to here is 6. That means your margin of error is 3. That's the half width, right? So this is the same as 22 plus or minus 3, right? That can be written like that. And if that's the case, of course that's not suggesting that mu is 21. There's just not enough evidence. There's not enough evidence to suggest mu is not equal to 21. There's not enough evidence to suggest mu is not equal to 21. I was afraid of that. Okay, well, the power just got shut off in my office. Hang on one second. Oh.
You should get paid extra tonight, I think.
The entire power is off in my building. Okay, so this is what we're going to have to do. I mean, I can't even see my way out the door. Okay, what I'd like you to do is this. I still have some power. Actually, I'm going to give you guys, I'm going to make this the breakout. This will be great. I'm going to do this. Actually, we're going to think on the fly here. How good, yes, this will be good. This is what I'm going to do. I'm going to give you guys something to think about real quick. And that is, I'm going to share my screen. I'm going to post this to Canvas. And then that'll be that. Share. Good gosh. Okay. So, what am I going to do? That's what I'm going to do. I'm going to take this thing, file, no, it's not file. I need to exit this. Okay, can you guys see my SAS window here? I just need to know that. I feel like you can see it. Can you see that SAS window?
Yes.
Okay, great. So this is what I'm going to do. Let's say I've got a question. Let's say my question is, I want to know if, I'm going to give you two things to do here. I want to know if the average shoe size at SMU is bigger than, say, 12. Oh, 10. I want to know if I want to open up a shoe store. I want to know if the average shoe size at SMU is bigger than 10. So what do? I go and take a sample. So data shoe, I'm going to set up a data set for you here. So input shoe size. So shoe size should be awesome. And then gender. And then, so I take my sample. And in that sample, it turns out to be, I get let's say I get somebody has a 9, and that's a male. Let's say that I have a 10. In fact, if you want to copy this down as I'm doing it, I'm going to post this to Canvas while I go find another spot. But, you know what? Maybe I don't have to move anywhere. Yeah, that'll just take time. If you would, well, I'll just kind of step through it. However you feel like you want to do this, go ahead and do it. But I'm going to type this out. There's not going to be much data. So I've got a male that's a 10. Let's say I've got a male that's a 12. Let's say that I'm just taking a random sample. Let's say I've got a 7, which is a female. Let's say that I've got a 9, which is a female. Let's say I've got a 5, which is a female. And let's say that I've got a 10, which is a female. And I just have that data. And I'm going to go in there, and I'm going to first, in fact, if you would, this will be good. You can just watch me on the screen, and I'll post this to Canvas. But or you can get onto SAS On Demand or whatever you use for SAS and just type what I'm typing in here. So for now, that's that. I'm going to come over here to SAS. Oops. Come over here. Where is it? To SAS. I'm going to start a new file, new program, and there is my data. Always what I'd like to do is say print data equals shoe. This is how you would do it, and run. I always recommend doing this because I've written tons of code in the past, and I thought there was a problem with the code, and really just the data didn't get entered right. So we do that. We look at our data set. It's a very simple data set. Looks nice. So now what we're going to do is we're going to say, okay, great. Now what I'd like to do is test what I just did there. So I'm going to do a proc t-test data equals shoe. And I'm going to do, I don't care about gender right now. I just want to look at the overall mean. I'm not breaking it up by sex or gender. So I'm just going to say var shoe size. I'm sorry, var shoe size. And I'm going to basically just run that. And what we're going to see in the end there is, so I'm just going to kind of lean on, hopefully, if you got any questions, let me know. But what I'm going to do here is I'm going to say, run this. And you'll notice here that we think that the p-value, we're going to come back to this, to the p-value in a second, but notice we have a 95% confidence interval from 6.75 to 10.9545. So under this, think to yourself, would you reject or fail to reject the null hypothesis that mu is equal to 10? Would you reject or fail to reject the null hypothesis that mu is equal to 10? And I can, so hopefully what you said is if you're looking at the null hypothesis that mu equals 10 versus the alternative that mu is not equal to 10, 10 is a plausible value on our 95% confidence interval. Since 10 is a plausible value, we're going to fail to reject the null. We're not going to say that the evidence suggests mu equals 10. We're going to say that we cannot, there's not enough evidence to suggest that mu is not equal to 10. And we're going to say there's not enough evidence to reject the null hypothesis that mu equals 10. but we're not saying that mu is equal to 10 because that's not what we're saying, right? We're saying it's somewhere, we think it's somewhere between 6.7 and 10.9. Okay, so let's come back to this example here in a second. I'm going to go back to our wall. We're making progress here. We're just going to keep on rocking. So I'm going to come back here, and I'm going to go back to my PowerPoint slide and check this out. Notice, okay, this is great. This never happened before. We have a dark screen and kind of a ghostly figure on the screen, but I think it's going to be great. From here on, it's going to be fantastic. So we've got our null and alternative hypothesis. We're going to draw and shade to find the critical value. We don't use the data here. We're not using any data. I'm just drawing what I think the distribution of sample means is. And I think it's normal. Why do I think it's normal? Again, this is for the beachcomber problem. This is for this beachcomber problem here. This is the same data. And I'm going to ask this question. I identify the null and alternative hypothesis. And my second step is to draw and shade and find the critical value. And I'm going to come on here and draw. I'm going to write this null and alternative hypothesis up here. This is HO mu equals 21. Put a little colon in there, versus HA mu is not equal to 21. That is a crappy, bad, not equal sign, but you get the idea. Okay, so we got HO mu equals 21 versus HA mu not equal to 21. That's what we're testing. So whatever it is that's up here, that's what we put here. We think under the null hypothesis, remember that p-value. Under the null hypothesis, we're going to say that mu is 21. And our whole strategy here, is to say if mu is 21, is what we observed, does that agree? Is that consistent with mu being 21, or is that not consistent with mu being 21? So what I want to do here is to ask you a quick question. I'm going to come away from the Comer example real quick and just say this. It's just about assumptions and probabilities. If I told you that I won the lottery 10 times in a row, I said, hey, I won the lottery 10 times in a row, what would you say? Would you think that I cheated or that I didn't cheat? Would you think that I cheated or that I didn't cheat if I won the lottery 10 times in a row? Just fire it in on the chat window. I'll know when to keep. Okay, great. I'm with Priyanka. I think I cheated. Doesn't mean I did. I could do it. Hopefully everybody agrees that it is possible. But why? Think to yourself, why is it that you think that I'm cheating? Think about what's going on in your mind. And this is what's going to explain the p-value perfectly. When I won 10 times in a row, and see if you agree with this statement. So I told you I won 10 times in a row. I agree that I probably think I would be cheating too, because what you're saying in your head is the probability of winning a lottery 10 times in a row is really small. Not possible, but it's really small. And the piece that we always leave off, right? Hopefully that's probably what almost everybody in the room would say. What's different is we always leave off our assumption. The probability of winning the lottery 10 times in a row is really small, assuming that I'm playing fair, right? That's our assumption, that we're just assuming it so much that we don't even say it. But if the probability is so small, that's evidence against my assumption. And my null hypothesis is always my assumption. And the p-value is that probability. So match it over. So if your null hypothesis is that I'm playing fair and your alternative is that I'm cheating, right? You can write that down. HO, playing fair, HA, cheating. And my p-value for the evidence would suggest that if I am playing fair, the probability of me doing what I did, winning 10 times in a row, is really, really small. Say it's 0.0000003. It's not impossible, but it's very, very small. It's actually way smaller than that. But the probability is 0.0000003. So what are you going to do? What did you do in your head? You rejected the null. Doesn't mean that I didn't cheat or that I did, but you rejected it. The evidence, since I have a small p-value, I reject the null. And that's what I'm going to do. That's exactly what I'm going to do here. Since I had a small p-value, I rejected the null that I was playing fair. The evidence suggests that I'm cheating. I didn't prove that I'm cheating, but the evidence is suggesting that I'm cheating. The whole point here is that the p-value is of observing something as extreme or more extreme, winning the lottery 10 times in a row, by random chance, because that's what a lottery is, under the assumption that the null hypothesis is true, under the assumption that I'm playing fair. And again, that p-value is very small, so I reject the null. That's what we're going to do here. I'm going to assume that it's 21. I'm going to assume it's 21, and I'm going to see if the evidence is consistent with that or not. So let's do it. That's what we think it looks like. How am I going to find those probabilities? I'm very good at finding probabilities under normal curves. I'm not good at finding probabilities under distributions that I don't know what they are. But if I know it's normal, I'm very good at finding those probabilities, which is why it's so important that we have the central limit theorem. So here it is. We know that the original distribution was normal. So we know that this sample of size 10, those means should be normally distributed. So what I'm going to do at the alpha 0.05, this is a two-sided test, so I split this into 0.025 over here and 0.025 over here. And what I'm going to end up doing is, some of my things aren't popping up here, but this over here, this is 2.5%. This is 2.5%. This is the way in SAS that you can find those quantiles. You can also do it however you did it in the past with calculators, or you can go online to something called StatTrek. It'll find it for you. But this number here is 2.44691. This number here is negative 2.44691. And those are the critical values. That's saying that many standard deviations away. If what I see ends up over here, that's going to be very rare. If what I see ends up over here, way less than 21, that's going to be very rare. If my test statistic ends up in here somewhere, that's consistent with it being 21, and I'll fail to reject the null. Anywhere out here wouldn't happen very often if the mean was 21, so I will reject it. It's as simple as that. If it doesn't happen very often under the assumption, then I'll reject. And if it does, and so we'll get there. The areas under this curve will be the p-values, but I'll show you that in a second. Okay, so here's what the picture looks like under step 2. Again, my critical values are 2.447 and negative 2.447. SAS will give you these values. My degrees of freedom for a one-sample test are 7 minus 1. Here which equals 6. Find the test statistic. So I had this in the quiz. The test statistic is simply x bar minus mu divided by s divided by the square root of n. This s divided by the square root of n is the standard error. This is the mean. That's what a test statistic will always be. It's an estimate minus the estimate. So I'm sorry, it's the estimate minus what we think it is. So it's the estimate minus the parameter divided by some measure of standard deviation. It's what's called scaling, or it's finding a test statistic, which is just a scaled version of your estimate under the assumption that you know mu and under some estimate of the standard error. So what we do when we get all that, we find that that test statistic was right here. I'll come back to that in a second. We find that that test statistic was 5.2 minus 4 divided by 1.7 divided by the square root of 8. Square root of 8. We would like to claim the population mean is greater than, oh, this is an old. This is, hang on one second. Okay, well that should be, that should obviously be, hang on one second. Going. All right, I've got the, I apologize. There's nothing to say about that. I've got the wrong version of that on there. That's the somehow that one got put in there. Let me just share my screen. I'll take you out to the real one. So what I'm going to match this to the SAS here in just a second. So start sharing. Let's go with stat 5371, this guy here, these lectures there, chapter 2, let's grab this guy, and all right, if you can see this, Let's go through this. Yeah, so this is the one with all the stuff on it. So here's your null and alternative hypothesis. All right, we've been through this piece. That's the 7 minus 1 is 6. We're up to this piece here. We've got our test statistic, which is 3.331. Here is, again, the null and alternative hypothesis. This one more time. Why is fall 2016? All right, well, this is, let's go on to the next one here. So 1, 2, 3, 4, 5, 6, 7. Nope. Huh. Things are all jacked up. Well, so the problem is here that this write-up is a little bit janky. Okay. So, all right, so I'll just show you the problem. So the problem here is that this statistic here says that's 8. Well, obviously, that is a 7. And we know that n equals 7, x bar is 29.86. This guy here should be 29.86. This guy here should be 21. And this guy here should be 7.09. So great, we'll just kind of take our way through it. So if this is, so we want to know what this test statistic is. And that is exactly, oh great, the power's coming back on. So that is exactly how you find the test statistic, and that's exactly what SAS will tell us. So what I'm going to do is come out here and grab this data, and this is how I would do it in SAS. So I'm going to grab this guy, this SAS screen right here. I'm going to take this editor, and we're going to have our data. This is the beach, and we've got inputs, and these are ages, and I've got data lines, and I'm going to, oh good, lights are back on. That is nice. Okay, so great. So now that is the idea. So we've got that. We're going to do proc t-test, data equals beach. We've got var is ages, and we've got data. We've got run. Okay, so remember that lottery example I just told you. When I run this guy, notice that I get, there's my 95% confidence interval. Remember that 23 to 36. And notice that my t statistic here, I've got to tell it right now it thinks, right now this thing thinks that, that I'm testing mu equals 0. But what I want to do is test mu equals 21. So you have to tell it what you think mu is. That's what H0 is. So you type in here H0, mu equals 21. I run this guy, and I end up getting this guy. Oh, great. So my t value here is 3.31, which is what I had in the slide. Just didn't have the metadata right. And my p value is 0.0162. So good. So this should match here now. So this is 3.31, which is what we said earlier. This should be 3.31. And my p-value was 0.0, let's look at it again. The p-value is 0.0162. What does that mean? That means that there is a 1.6, if the true mean was 21, if the true mean really is 21, there's at a 1.62% of the time, we would observe a sample mean. We'd grab a sample of 7, and we'd observe a sample mean as extreme as 29.85, right? If the true mean is 21 and we take a random sample, we expect the mean to be close to 21. Our mean was 29.8571, and this is saying that wouldn't happen very often, and that's what our confidence interval is agreeing with, is that we should reject the null and suggest this part here, that this p-value, if you can see it, that little red area right there, that red area is the p-value. And in a two-sided test, you're going to shade both because you're looking at the probability of being as extreme or more extreme. And even though the test statistic was up here at 3.31, negative 3.31 would also be as extreme or more extreme from 21, just on the other side, so we include that in the p-value. So the p-value here, again, is whatever it was, 0.016 something. It's smaller than 0.05, and that's the thing. Whatever alpha is what you're comparing it to, that's smaller than 0.05, so we reject. If it was bigger than 0.05, then we'd fail to reject. Please ask any questions. But that is that part. We can look at the p-value here real quick just to get a better idea of it. If we wanted to find the p-value, here is some SAS code that would help you find the p-value. Well, obviously, proc t-test will give you the p-value. There it is right there, 0.0162. Did I put, well, that's fine. There's other way. I'll show you during office hours how you can actually manually find it, but you don't need to manually find it if you can just run proc t-test. That's 0.0162. It's small, so we reject. So here's the final write-up. 0.0162 is smaller than 0.05, so we reject HO. There is sufficient evidence to conclude that the true mean age of patrons at the Comer at 7 p.m. is greater than 21. And the reason why we can say it's greater is because the test statistic, even on a two-sample test, wherever the test statistic is, you can say it's that direction. So if the test statistic ended up over here, that would be evidence that it was lower. If it ended up over here, it would be evidence that it's greater. But since it was 29 something, that's evidence that it's greater. So a 95% confidence interval, which we always want to include, is 23 to 36. That's what we think it is. And notice those are all bigger than 21. And the scope is, since this was a random sample, we can generalize these findings to the entire population of Comer patrons at 7 p.m. Notice there's no reason to make a cause or effect statement here because there was only one sample, right? They're not comparing it to a different sample. Does anybody have any questions on what I just went over here? Right after this, I'm going to kind of fire it up. I'm going to go into two-sample tests. And then we're kind of getting into the p-value idea, but I want to get into a two-sample test. And then I want to talk briefly about power, and then we'll be out. But if you think you've got this part right here, I'm just going to keep talking. Just interrupt me or fire in something on the line. Computer set up H greater than 21 because we're probably looking at drinking age. So okay, there's one thing is when you fire in a comment, it does, since I'm sharing my screen, I have to open up this special thing, but I just saw Josh's. You could, the thing with running a one-sample test, I mean a one-sided test, so what Josh is talking about here is a one-sided test. In a one-sided test, you're going to put alpha completely on the right side. You're not going to worry anything about the left side. So if you have like what Joshua has here is HA greater than or equal to 21, that's going to put alpha completely over here. And if you put alpha completely over here, that's going to make that that 2.447 is going to get smaller, right? Because this is 2.5%. When I make this over here 5% and take this away and make this 5%, it's going to make that 2.447 smaller. And when you do that, it makes it easier to reject, right? Because anything to the right over here in the critical value, anything more extreme than whatever that new value is going to reject. So So the reason why you would run a one-sided or two-sided test is if you were checking, if you had reason to believe that the true age at this bar was either 21 or greater than 21, which makes sense, then you would do that. The only thing you have to worry about is that somebody might come up and ask you about, actually, as we're going to get into, the power of your test, because it's easier to reject when you run a one-sided test. It's easier to reject when you run that one-sided test. And so it's more convincing if you run a two-sided test and it rejects than it is if you run a one-sided test and it rejects. And sometimes, like in some states, the judicial system will not allow one-sided tests. They'll only allow two-sided tests because of that reason. You could run it either way. To Josh's point, that's perfectly fine. That's perfectly sound. And as far as this course is concerned, if I asked you to run a two-sided test, you'd have to run this. But if I didn't, then you can run it either way. So that's a good question. So what I want to do real quick is take us through an example. Oh, so let's go back to the SAS window and look at what we had here. Oops, not there, right here. So this was when the power went out, this was the
Here we cannot see anything.
Uh-oh. You can't see.
Like there is a message saying nothing is being shared and everything is blacked out.
Which is a
It's
great
great.
thing.
Yeah, great.
Okay, I don't know what's going on. Yeah, I can't. Okay, stop sharing. I seem to be locked out. I don't know what's going on today, guys. I apologize. This has got to be the worst session I've ever had. But
it seems like your screen was slower. You know, it'd take a while to catch up, but this seems a little bit different.
Okay, it says connection lost. Let me get my connection back. If you have that code, though, if you had typed that code into SAS, that's what we're going to run. It looks like I got booted, so I'm going to boot back in here. I don't know what. All right. Join now.
I think somebody's messing with you. Not possible. We should do some sort of test to see if this is possible, all these problems.
Right. Well, that's a good. So under the assumption that no one's messing with me, what is the probability that we would have all these problems? And that probability might be small, and if that probability was super small, we would reject the null and conclude that somebody's screwing around with me. I don't know. My whole computer is like frozen. If I could just get... Well, let me say this. I hate to keep jumping around, but I can talk about this while my computer maybe fires up again somehow. Everybody that answered on question 3, I got a lot of questions on the quiz from question 3. If you answer the permutation test as probable, that's a totally acceptable answer, and I've already gone in and corrected those. So if on question 3, again, you answered that a permutation test is probably best for this data, a lot of people will only run permutation tests and will not run parametric tests. And I guess while I'm still talking about that, let's see here. I think I'm about to get back in. So let me say this then. Notice that in order to find the p-value, we have to know that it's a normal distribution, right? I showed you the picture of step 2. Step 2 is a normal distribution, and that red area underneath there was a normal distribution. We have to know it's normally distributed. If we cannot be sure that it's normally distributed, then those p-values will be incorrect. And what we're going to get into next week is if those are, if I don't know if it's a normal distribution, if my assumptions aren't met, then I won't know that step 2, that the distribution of the means is normally distributed. And if that's the case, how am I going to find my p-values? And the answer is, one answer is the permutation test. Some people run permutation tests most of the time. Because in a permutation test, I don't look at the area under the curve. I actually count how many I observed that were more extreme, how many that came up in the simulation that were more extreme than what I observed. You build the distribution yourself. You don't rely on some shape that you assume is true. So in a lot of respects, the permutation test is safer. Sometimes it can be slower, but in today's computing, not necessarily. Guys, nothing's happening on my end. So that's a big deal, though, is the permutation test is assumption free in that you don't have to assume that you have these normal distributions, that you have a normal distribution. I'm going to turn this off and turn it back on, turn Wi-Fi on. Let me see if I can get one more idea out here before we end this. I'm just reconnecting to my phone. Actually is, yeah. So, it's not connecting. Is it? So what we're going to do in the end here is, if I can, I'm going to show you an example of a two-sided test, and I might have to delay the power explanation, but I'm having a hard time even just connecting to the internet. Okay, well, here's what we're going to do. I'll finish out till 8 o'clock. I'd like to try to finish this idea if I can ever get this internet connection going again. I really apologize. We had this power thing, so I don't know really where to go, except for this. I know that everybody's got a busy schedule. I'm going to run additional office hours this week to try and make sure that everybody is on the same page. So, so I'm going to finish this out. Hopefully everybody's got a good idea where to go here. I'll come up with a time tomorrow and on Saturday to, I'm going to come up with a time tomorrow and on Saturday to basically do this again. So you can come to both if you want. If you can't make either, let me know and I'll come up with something else. But I really apologize for this one. And the only way I know around it is I'll run, my office hours will be Sundays, 5 to 6, from 6:30 to 7:30. So office hours are on Sundays from, what I said to say, 6:30 to 7:30. So that's the way it'll always be for this class, 6:30 to 7:30 on Sundays. But I'm going to run 2 additional, probably just 1-hour sessions to try to get us all on the same page here. So I'm sorry for the additional time, but if you can ring in, that's good. I'll video them all so you can check those out. I'll basically just do a cleaned up example of what's going on in here and answer any questions. So I have got internet connection back. So let's see if we can make this work one more time and finish with a little bit. 2DS. I don't know. It's still not working. This is on. All right, let's do this. All right, got one more idea. We'll just go until 8 and hopefully we'll get something out here. I'm going to log in on the Windows side to DS. I just don't know. I don't have an internet connection. There's no internet connection. There's an internet connection. All right, guys. I don't have an internet connection. I don't know what's going on. So I can't log in. But in this last couple of minutes here, let me ask you this. Go ahead and just we'll make good use of this last 10 minutes. That'll help us when I do it again, either on Friday or Saturday. Or if you come to both, that's great too. I remember last week we had a splurge, so I'll make sure that I get a secure connection. But I can tell you, we've never had this problem before. So what I'm going to do is ask you this. If you got a sheet of paper, let's do this. Let's say, this would be great. Write down this. Write down HO mu equals 5, and I'll write it with you, so I've got it here. Write down HO colon mu equals 5, and under that put HA mu not equal to 5. Okay, and if you've got that, I'm just going to make up some statistics here. Let's say that your step 3, let's say your test statistic, let's go, I'm sorry, that's step 1. Let's go to step 2. Let's say your critical value is negative 1.96 to 1.96. So you've got 2 critical values, negative 1.96 and 1.96. And let's say that your test statistic is 2.4. So my question to you is, once again, you've got HO, mu equals 5, HA, mu not equal to 5. Number 2, your critical values are negative 1.96 to 1.96, or negative 1.96 and 1.96. Your test statistic is 2.4. I want to know, question 1, is the p-value bigger or smaller than 0.05? Let's say alpha is 0.05. So your alpha is 0.05. I want to know if your test statistic, if your p-value is bigger or smaller than 0.05. Question 2, I want to know if you're going to reject or fail to reject the null hypothesis. And question 3 is, can you write a good conclusion for that problem? Can you write a good conclusion for that? So we'll just do a couple of these and we'll get out of here. Ooh, this is good. I like these kind of conceptual questions. So once again, you got HO mu equals 5, HA mu not equal to 5. Your critical value is a normal distribution. On one side, you're going to have negative 1.96. On the other side, you're going to have 1.96. Now go ahead and plot your test statistic of 2.4. If you've drawn that normal curve, if not, just think test statistic of 2.4. So your p-value, since your test statistic is more extreme, is bigger than 1.96. That means if you were to draw a line there and shade the area of that normal curve to the right, it would be very small. That means your p-value will be smaller than 0.05. If your test statistic is more extreme than your critical values, your p-value will be smaller than alpha. So the first question of 1 is the p-value is smaller than alpha. If your p-value is smaller than alpha, that means you're going to reject the null hypothesis. That means you're going to reject the null hypothesis. And finally, if you reject the null hypothesis, then your conclusion is something like this. There is enough evidence to suggest that mu, the mean of whatever it is, that mu is not equal to 5. Now, instead of saying mu not equal to 5, if this was shoe sized, you would say there's enough evidence to suggest that the mean shoe size of SMU students is not equal to 5. And since your test statistic was 2.4 and not negative 2.4, that would be enough evidence to suggest that the mean was greater than 5, since it was on the right side. If mu was negative 2, or if that test statistic was negative 2.4, that would be evidence that it was less than 5. But okay, so let's do another one. Oh, let me ask you this one. Let me ask you this. Would the confidence interval contain 5 or not? And I will get to this next week, but a 95% confidence interval is what we'll always agree with an alpha 0.05 two-sided test. Probably get to that on Friday. But when alpha is 0.05 for a two-sided test, you're talking about a 95% confidence interval. So what we have up here, would a 95% confidence interval contain 5 or not? And the answer would be, since we rejected HO, it would not contain 5. 5 is not a plausible value of the mean. 5 is not a plausible value of the mean. We rejected it. Of course it's not. So it would not be in the confidence interval, because the confidence interval contains plausible values. So going up next up, let's write this one down, and I'll convene right here at 8. We got about 5 minutes. So HO, let's say mu equals 117.2. HO is mu equals 117.2. HA is mu not equal to 117.2. Okay. So step 2, let's say my critical values now. Let's say alpha is 0.01. So alpha is not 0.05 anymore. Alpha is 0.01. And let's say that means my critical values are going to get bigger. So let's say my critical values are now negative 2.57 and 2.57. So since alpha is bigger, my critical values are going to get more extreme. because they're further out in the tails. Okay, now let's say that let's just do what we did before. Let's say my test statistic, let's say I get my test statistic back. I can calculate it by hand, or I can look at it on SAS. Let's say my test statistic is negative 1.2. Same questions, 4, 5, and 6. I'll give you a second to think about it. Try to write it out. Number 4 is the p-value bigger or smaller than alpha, which is 0.01? Number 5 is, am I going to reject or fail to reject HO? We're always going to reject or fail to reject HO. And number 6 is, can you write up, maybe the most important, they're all important. Number 6 is, can you write a conclusion about mu? Let's say mu is the average body temperature of a giraffe. How's that for random? Let's say we're testing the average body temperature of a giraffe. And we think it's 117.2 Fahrenheit. Okay, so I'll go slowly here. If you're writing number 6, it does take a little time. But number 4 is since the test statistic is not as extreme as the critical values. What we're seeing here is evidence that is consistent with mu equal 117.2. It's not in the rejection region. It's closer to the mean. It's closer to normal. It's closer not to normal. It's closer to the middle. It's not rare. So my p-value would be bigger than alpha. My p-value would be like 0.294 or 0.376. And it's saying the same thing with the p-value. The probability of observing something as extreme or more extreme than what was observed, given that mu is truly 117.2, that probability is high. It's consistent with it being 117.2. So my p-value here is bigger than alpha. It's bigger than 0.01. If my p-value is bigger, I'm going to fail to reject mu equals 117.2. I'm going to fail to reject mu equals 117.2. And in that case, my conclusion here is there is not enough evidence. There's a lot of ways you could write this, but the conclusion is there is not enough evidence to support the alternative that mu is not equal to 117.2. And we have to write it, we have to either write it that way, I'll say that way again, there is not enough evidence to support the alternative that mu, the mean temperature of giraffes, is not equal to 117.2. Another way to say that is there is not enough evidence to reject the null. There is not enough evidence to reject the null that the true mean temperature of giraffes is 117.2. Nice. So that's it. Notice that we have to say it that way because we're tempted to say the evidence suggests that mu equals 117.2, but that's not what the evidence suggests. There's a confidence interval there of plausible values, and that's what it's suggesting it's between. We can't pick out one of those values, and so there's that. So the final one is there's not enough evidence to support the alternative that the mean temperature of giraffes is 117.2, and then put the p-value at the end. You're always going to put the p-value in the conclusion. Always put the p-value in the conclusion. And my final question is, if I found, think about it, I got two questions. One is, for alpha 0.05, notice I'm dealing with a two-sided test here. And you can tell it's two-sided because the alternative is not equal to. Joshua, earlier, if you look at his comments, had mu greater than 21. That would be a right-tailed test. Mu less than 21, that would be a left-tailed test. If it's not equal to, that's implying a two-sided test. So since I'm in a two-sided test here, both these were two-sided, alpha 0.05 was a 95% confidence interval. And that will always agree with the hypothesis test. If I reject, then the null will not be in the interval. If I fail to reject, the null will be in the interval. So over here in the giraffe one, I failed to reject the null. My question is, A, what is the appropriate confidence level for that test, that alpha is 0.01? And B, will 117.2 be in that interval? So question one, what is the appropriate confidence? Is it 95? Is it 98? Is it 97? Is it something I haven't said? What is the appropriate confidence level? And will 117.2 be in that interval? The answer is a 99% confidence interval, which is wider than a 95% confidence interval. But a 99% confidence interval will always agree with this test. And since it always will agree, since I failed to reject the null, that's saying there's not enough evidence to say that 117.2 is not the mean temperature of these giraffes' bodies. So since we're saying that 117.2 is a plausible value, we're not saying it is the value. We're saying we're failing to reject it. We're saying it's plausible, so it will be in the interval. It will definitely be in the 99% confidence interval. So one more time, 99% confidence, since we failed to reject, 117.2 will be in the interval because 117.2 is a plausible value. Okay, I hope that was useful. If you understand that, you've really come along, you're really a long way down the road. What we're going to do on Friday or on Saturday, and I'll give you the times of those once I figure out my schedule now, but what we're going to do on those is we're going to address 2 sample tests, which is really the point of the chapter. We're going to address 2 sample tests. The only difference is that instead of testing mu equals 117.2 or mu equals 5, we're going to be testing the difference of mu's, mu1 minus mu2. And just to get you to come down that road, because you've seen it before, what we're going to be testing really is the null that mu1 equals mu2. That's what we're thinking that we're testing. Is mu1 equal to mu2 or is mu1 not equal to mu2? And the key is, and I won't go on beyond this, I know I just keep rambling here, but if we're testing mu1 equals mu2, if 2 things are equal, what is their difference? If 2 things are equal, what is their difference? And that's what we're going to test. Notice if 2 things are equal, then if mu1 is equal to mu2, then mu1 minus mu2 will equal 0. And if mu1 is not equal to mu2, then mu1 minus mu2 will not equal to 0. So the value that we're going to test is an x bar. It's going to be x bar 1 minus x bar 2. Is that consistent with the difference being 0, or is it consistent with it not being equal to 0? I'm going to show you, I'm going to post some slides tonight so you can look over those examples. Please look over those examples, and I'll come up with a time tomorrow, an hour tomorrow, and an hour on Saturday that we can iron this out and forget that this particular night happened. I really apologize. But don't forget what we learned, because we got a good start here. So, is anybody left in the room? Because I can't see anything.
Pretty sure most everyone is still here.
Okay.
We are here, Bivin.
Okay. Well, good work. Does anybody have any questions on the way out that we can talk about?
Do you know when the homework 1 grades will be posted?
Yes, they will definitely. Every week they'll be posted before you get before you submit. Hopefully way before, but you'll always get them back before you turn in the next homework. So all I can say is this week is our online semester started before our on-campus semester. So our TA is getting back in town. So so he'll have them graded. I've got him working on it now. So you'll probably have them by Saturday, but you'll definitely have them by Sunday. And most times you'll have them back by, if you turn them in on Sunday, you'll have them back by Tuesday or Wednesday.
Okay.
Cool. Good question. What else did I want to say? I guess that's about it. I'll have office hours are always Sundays from 6:30 to 7:30. I'll have an hour tomorrow, and I'll have an hour on Saturday to get into the depths of this. I'll record both of them, and so if you can make it, please make it. If you can't, then check the recording. And if you want to talk to me, then I can make an individual one for you if you really got some questions that you want to have answered in person. So that's it. If there's no more questions, I will see you guys tomorrow or Saturday. And I will do everything possible with this. Yes.
Okay, so the homework for today is the one which we talked about here right now, or are you going to be posting something else other than this? And when it will be due then? The same 11:59 Friday?
Yeah, 11:59 Sunday.
Sunday, sorry.
Yeah, sorry, 11:59 p.m. on Sunday Central Time is when it's due. I can't see it right now because my internet's down, but if you go online, it should be, Unit 2 homework should be posted on 2DS, and I'll also post it to Canvas. But it should be out there on 2DS right now. Does anybody see that?
Yeah.
Yeah, we see it in the 2DS.
Yeah, it's out there.
It's posted.
Okay, yeah, I'll end up posting. Everything you need should be on the 2DS website, but I will also, as always, post it to Canvas as well. So when you look in there, you'll be able to see the same exact thing. But does that answer your question, or did I miss it?
Yeah, I'm good, Evan. Thanks.
You're good. Okay, cool. All right. Sounds good. I'll see you guys next week. This is kind of odd without seeing everybody, but
Hey,
I'll do it here.
Bivin, this is Justin.
Yeah.
A question. So for the discussion boards, do you want that on the wall, or do you want it under that? I guess like Unit 2 discussion boards, or how do you? I just did clarification.
Yeah, that was written into the syllabus for everybody, and every instructor does things a little bit differently. That's for you guys. I'm not going to require that you guys post to the discussion or to the wall, but I really encourage you to do it if it helps. If it helps you. So just kind of figure out, or if you want to do it on a WhatsApp thing somewhere else. So I encourage you to kind of do that, but you don't need to. Your grade isn't based on any of those. What I am going to check though is the questions that you answer for the asynchronous ones online. Those are really important for your grade,
Okay.
and I think otherwise. So yeah, you don't have to post to the discussion board. You don't have to post to the wall, but I think it's really helpful to have some way to communicate in that fashion. Cool.
Sure. Thank you.
No problem. All right. Well, again, guys, I really apologize. I like to run a good live session. I have a lot of fun in these things. But we'll get back on track on Friday or Saturday. And actually, it may work out better if we can get smaller groups, and this is a good start. So and definitely look at the PowerPoint slides I'm about to post out there, so you can really ask questions on the way in. So we'll master this stuff and move it on forward to Unit 3, and just to keep things on track, I've never missed one. So you can make exploding noises if you like, but I'm going to. So last week was kind of weird too because I was invisible, so I don't know what's going on. But okay, I'll see you guys on Friday or Saturday. I'll post those tonight, so in the morning you'll be able to see what time those will be. And nice work tonight. Thank you for sticking with me. Hopefully you got something out of it. That's it. A 1, a 2, a 3. Bam!
Woo!
Good, made you feel good. All right. Thank you. See you on Friday, guys. Good night.
Yeah. Good night.
Nice.
Good night,
Good
everybody.
night.
No, yes.
Good night, bye.